Now, when you want to draw a critical path method network, first of all, you must develop the project network, then construct the project network, then compute the process of forward pass, backward pass, and float, and then lastly, we identify what we call the critical path. Um, Essentially, in a nutshell, an event is circular with the event number, then the earliest start time or earliest finish time on the top right quadrant, and latest start time or the latest finish time on the bottom right quadrant. The difference between the earliest finish time and earliest start time depends where you're looking at an event. Like we have the event on the right, which is an event A, and this event is an arrow. You can see that the arrow is pointing towards a particular direction, and we have what we call the head of an arrow and the tail of an arrow. So if we are using earliest start time, we'll find that that particular event will be at the tail of that particular activity. If we have what we call the earliest finish time, that event will be at the end of that particular activity. So these terms can be used interchangeably, meaning that the earliest finish time of one activity will also be the earliest start time of the next activity, and so on and so forth. So with that in mind, given a problem as shown below, where we have a set of activities, their duration and their predecessor activities, and we are told to draw a network, the first thing we have to do is we have to construct this particular network. We have, first of all, the trick here is to try and pass through all the activities and identify events where the activities will be converging or diverging. Like we have activity C, where we can see that there is a convergence of activity A and B, and also activity E, where we are seeing convergence of activity C and D, and also activity H, where we are seeing a convergence of the same. So we are using slightly modified diagram for the network. It's not exactly the same as the one that we had in the past, but in this particular case we have activity A taking 7. Remember that it's starting at the initial node, or it starts at time 0, and it takes 7 time units. So we'll have it start at event number 0, start at the earliest start time for that particular activity will be 0, and the earliest finish time will be 7, because the duration of that particular activity is 7. The same will happen for B, which will start at 0 and 2, and the event will be number 2. Then when you come to activity number C, we'll find that we have a convergence. We have a convergence of 2 branches. We have convergence of A and B. So when we're calculating the earliest finish time, we always take the largest value. Now that does not become a problem, or it does not prop up so much until you get a convergence such as at event number 2, where we are bringing A and using a dummy, combining it with B to get C. So what happens there is that we'll have activity A, which takes 7, versus activity B, which takes 2, and we look at the one that has the larger time. Now the one that has a larger time, the one that will have a larger time will have its value drawn on the top right quadrant of that particular event, which is event number 2. So we'll have 7 versus 2, and definitely in that case you'll find that 7 will be larger than 2, and therefore we'll have 2 drawn there. So this particular activity, which is activity C, will start at 7, and it will take 11 time units, and it will terminate at 18. When we go to the next activity, we'll find that we have D, and D starts from the initial event, which is event 0, and the reason why I've combined it with C is, if you look slightly ahead, you'll see that E is a combination of both C and D. That's why it has allowed it. I was prompted to add it there. Alternatively, I could have added, if I did not look ahead, I could have added maybe on the top on top there. But the problem is that when I add, when it reaches the time for plotting that convergence where we are getting activity E, I'll have a challenge. So I decided to have it where it is shown. So when you have activity E as per my arrangement, you find that it becomes a bit easy, because if I was to have the other one on top there, you can imagine now having it coming all the way down, meaning that we can no longer have any other activity coming from these other events, which we'll see later on. So when you come to F, something interesting happens. F starts at C and terminates at the event which will cause G, which means that it will terminate at this particular event. Also E starts at C and D and terminates at this particular event. So since F is only dependent on C and E is dependent on both C and D, I'll isolate C, use it to generate F, then link that event using a dummy, then combine it with D and have E as shown. Okay, let me give some time for that to think. I repeat, since F is only dependent on C, whereas E is dependent on D and C, what I'll do is I'll isolate C, have F emanate from C, then bring C using a dummy, combine it with D in order for me to have E. Okay. Then when we move forward, we have G, and G emanates from convergence of both F and E as shown. So we'll find that as I progressively drew my network, I also filled in the times, that is the earliest start time or the earliest finish time. That is for a case, for instance, activity number A, the earliest start time is 0, earliest finish time is 7. For activity G, earliest start time is 33, earliest finish time is 36. When you move forward, you find that now we do what we call a back pass. We now fill the latest finish time and the latest start times. Now, since we are starting from the end event, you'll remember that when you're talking about the end event, it's called the latest finish time. When you're talking about the tail event, it will be the latest start time. And what I'm talking about here is when I look at G, the end event here, so that is the end of the arrow. The end event will be this event number 6, whereas the tail event will be this event number 5. So the latest finish time and the earliest finish time must be equal. Okay, so this one is 36 and I also have 36 on the other side. Remove the duration and that will give me the next thing, which is going to be 33. And now I keep on working back. 33 minus E, which is 15, will give me 18. 33 minus 7 will give me something, and I will add 18. But when you come to this other point, when we are working with latest finish time or latest start time, we look at the time which is smaller. We don't look at the one which is larger. When we are doing the earliest start time or the earliest finish time, we are looking at we are taking the larger value. When you are looking at when you are working on latest finish time or the latest start time, we take the smaller value. So it will mean that when you have 33 minus 7 versus 18 minus nothing, you'll find that 18 minus nothing will be the one that is drawn there because it is smaller. 33 minus 7 will leave us with around 26, which is larger than 18. Using that criteria, we keep on passing back and fill the rest of the times until we reach the initial event. point to note is that you'll discover that there are some events which have the earliest start time and the earliest finish time balancing, that is being equal, like event 0, event 1, event 2, event 3, event 4, event 5, event 6. Now, these events will be this implies that these events will be joined by a critical path, or these particular events will be joined by a critical path. Either you'll have a critical path emanating or from that particular event, or terminating in that particular event. So this is it's not a must that event will have both times being equal. In most cases, actually, you may find that the times may be different, but when you're looking at the activities on a critical path, you'll find that those times will be equal. Now, that will help us identify where the critical path is. So, the first, after having that, we now join those events which are on the critical path. Now, we have two activities here which are interesting. We have A and B, and A starts at 00, stops at 77, and then we have B starting at 00 and also stopping at 77. So which one is going to be the critical path? Is it going to be the upper one which has A, or the lower one which has B? Now, B has a duration of 2, whereas A has a duration of 7, meaning that B can be delayed without delaying the overall network, whereas A cannot be delayed without delaying the overall network. Therefore, A is on a critical path, and we'll confirm that by adding the activity A having double lines, and also the dummy which connected A to B having double lines. The process will be repeated to the other activities up to the end of the diagram. Upon conclusion, you are required to identify the critical path by setting the activities that are on that particular critical path. So in this case, we are going to have activity A, C, E, and G. Now, somebody may ask, why are you not including the two dummies? If you remember, the definition of a dummy activity is that it does not consume time or resources. Therefore, if you have a critical activity passing through a dummy, that dummy will not be represented because it does not consume time or resources. Essentially, what it does, it allows you to convey the finish time of one particular activity to the start time of the next activity. That means, for instance, from this particular event 1 to event 2, and then from event 3 to event 4. So that is how you can draw a CPM network. There are other things that you will discover in the network, is that activity B, activity D, and activity F can be delayed without delaying the entire project. That means those particular activities have what we call float, and float is the free time available for a activity to complete, the additional time that is available for an activity to complete without delaying the project. So you'll find that the activities that are on a critical path, even if one of them is delayed, for instance, if I delay activity C by 1 second, that means instead of terminating it at 18, I terminate it at 19. The entire project will be delayed. But what will happen if I delay activity F by something like if I delay it by something like 4 seconds? You'll find that it will not have any impact, because 4 plus 7 will give us 11, 11 plus 18 will give us 29, and 29 will be smaller than 33. Therefore, it means that it can even delay for a further 4 seconds without delaying the entire project, without going critical. Okay, so the free time or float is the time available for a project to complete, additional time that is available for a project to complete or an activity to complete. Let me correct myself there. That is the additional time that an activity has to complete without going critical or delaying the entire project. So non-critical activities in this case are B, D, and F. And that marks the end of that problem. So as soon as you have your diagram drawn, you've identified the critical path, you've properly done the forward pass and the back pass. You'll also have calculated the earliest start time and the latest finish time, and identify the critical path. In such a problem, you will be done with that particular problem. There can be no further addition on that. Thank you.